So let's see why we get these glacials and interglacials. Of course, the climate system is incredibly complex. There's many things that go into driving Earth's climate system. But let's look at the Pleistocene, Ice Age, and interglacials a little bit. So first of all, we have this long-term decline of temperatures from the Mesozoic, right? So Mesozoic is back here, right? This is the extinction of the dinosaurs right there. We had this warm event in the Eocene, and really since then, temperatures have been in decline with a few little bumps on the way, as I said. So why did this happen? Well, we do have a carbon dioxide drawdown by silicate weathering, as we had many of these major orogenies, these major mountain building events, especially things like the Himalayas. So what happens as mountains are uplifted, you get a lot of chemical weathering occurring on those, right? Again, Earth is always in balance, so if we lift things up, there's going to be a force that's acting to erode them away. That's our chemical and mechanical weathering. But when you have chemical weathering of silicate minerals, you have a chemical process that actually takes up CO2 out of the atmosphere. So our carbon dioxide levels in the atmosphere drop significantly. Remember, back in the Cretaceous, they were as high as almost 4,000 parts per million, and they're around 400 parts per million today. So major drawdown of CO2. But then we also have, on top of this, we have those glacial interglacial cycles. So overall, this is a really cold time period on Earth, but it's punctuated by these kind of slightly warmer times, these interglacials, like what we have today. And the thing that really drives these are Milankovitch cycles. Milankovitch cycles are variations or cycles in Earth's orbit. And as Earth orbits the Sun, it undergoes changes in a regular cyclical pattern. And Milankovitch figured out that these affect the climate system. And so that's why they're called Milankovitch cycles. I always think that Milankovitch was an interesting guy because he was a prisoner of war in the First World War, and he gave his word that he wouldn't try to escape and fight again as long as he was allowed to do his science research. And so they basically were like, okay, you can do your science research, and that's how he spent his POW days in the First World War. So anyway, there's these three parts or three cycles that are part of the overall Milankovitch cycles. And it's eccentricity, obliquity, and precession. Now, Milankovitch did not discover precession, also called precession of the equinoxes. This was actually known to the ancient Greeks over 2,000 years ago. But what are each one of these? Okay, in eccentricity, Earth's orbit goes from being circular to getting more and more elliptical and then going back to being circular over time, right? And being a cycle, it goes back and forth between these two. So the orbit gets more and more elliptical and then more circular, and then more and more elliptical and more circular, back and forth and back and forth. Now, our next one, obliquity, that's tilt of the Earth's axis. So the Earth's axis, the tilt of it varies a little bit, and this is going to affect the amount of energy the polar regions get. And this is important when we're looking at ice ages because glaciers start growing from the polar regions, right? So if those are getting less energy, we're more likely to have glaciers start growing. And then we have precession of the equinoxes. And if you ever get one of those little toys, the top, and you spin it, you'll notice the axis kind of wobbles around. Well, Earth's axis wobbles around as well. And that's what precession is. And so this precession right now, for example, the pole star is Polaris, right? The North Star. But as that axis wanders in this precession of the equinoxes. Eventually, I think Vega is going to be our pole star, and then it'll go back to being Polaris again. And so it's constantly the pole is kind of wobbling, and again, this is going to affect the incoming energy to the polar areas. So overall, this affects insolation. Insolation is the amount of energy reaching Earth's surface. It can affect the amount of energy up to 20% in North Polar regions, allowing glaciers to end up growing. Now, another important aspect to Earth's climate system is this thing called thermohaline circulation. This occurs in the world's oceans. Thermo refers to temperature, haline refers to salinity. Now, both temperature and salinity affect the density of seawater. Cold water is denser than warmer water. Saltier water is denser than fresh water. And these density changes of water drives the movement of ocean currents. Remember, ocean currents distribute heat around the planet. So if you alter the ocean currents, you can end up altering which parts of the Earth get warmer or colder temperatures. This is our basic thermohaline circulation. We can see warm water currents, and then in red, and cold water currents in blue, and some are surface currents and some are deep water currents. But basically, these are constantly circulating around our planet, distributing heat around our planet. One thing that's thought to have happened, we had this time period called the Younger Dryas, that basically Earth was warming into the current interglacial, and it suddenly plunged into a glacial time again for about 1,000 years, glacial temperatures. And part of what's thought is that the Gulf Stream was shut off because of things happening up here, and that prevented warm water from getting up there, and so we had this brief but sudden return to glacial temperatures, all because this thermohaline circulation was disrupted. So this is an important driver in the climate system. Now, what I'm showing right here, this is a temperature record from 100,000 years ago to today. About 110,000 years ago was the last interglacial. In Europe, it's called the Eemian interglacial. Temperatures were a little bit above where they are today. Then we get into this glacial time period. And one thing to notice about this glacial time period, this is what one of my colleagues calls the age of chaos. Because notice how fluctuating and how variable the temperature record is. Then we start warming up, then we have that Younger Dryas, cold, for about 1,000 years, and then we warm up into the current interglacial. And notice this current interglacial, while temperatures do fluctuate in there, overall there's a lot less variability than in the last full-on glacial, and it is, of course, also considerably warmer than that time. So interglacial or interglacials tend to be warmer with less variability in temperature, and glacials tend to be colder with more chaotic variability in temperature. So overall, in the Cenozoic, we really end up shaping North America into the landscape we see today. And this is Western North America, and even without having that map of physiographic provinces, you can start with a careful eye picking out things like the Rio Grande Rift, the Basin and Range, the Colorado Plateau, the Cascades going into the Sierra Nevada. You can start picking out those things. Oh, there's the hot spot, the mantle plume track of Yellowstone. You can start picking those things out if you start having an eye for looking at the Earth and reading its geology. And that brings me to the random picture of the day. That's of course me. I like whitewater rafting. I used to do it a lot when I lived in the western United States. This guy here, his name's Andrew. He had never been whitewater rafting because he couldn't swim. He spent the first part of the trip like holding onto my life jacket for dear life until I pointed out that the water was all of like 2 feet deep, and so if he fell over, he could stand up and not drown. So anyway, that was a fun trip. So signing off.